This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Hello everyone. Just a special announcement today. We now have a student rep. Linda, do you want to say something?
Yeah, hey guys, so I'm the student rep. Trevor's going to put my email address on Blackboard. If you have any suggestions on how lectures could be improved or tutorials could be improved, come to me. I'm not here for homework help. That's his business. But I'm here if you have suggestions. Cool.
Thank you. And yes, we'd love to hear as much feedback as possible. Can be positive, can be negative, particularly if it's constructive and ideas on what we can do better, what worked, what didn't, is very much appreciated. So yeah, we try and change it from year to year in order to make a better learning experience for you. So having your feedback would be great. Thank you. On to let me dim the lights. Okay, so today's lecture sort of dovetails into yesterday's lecture. We'll be talking about distributional semantics, which is one of the very hot areas in the last 6 or 7 years or so in language processing, and has now started to have a lot of impact in a whole lot of other fields. Okay, so just to motivate, so yesterday we were talking about lexical databases, things like WordNet, and as we pointed out, they're very expensive. They're manually constructed. Someone has to sit down by hand, have to go through text, they have to decide on what meanings are being used, they have to decide on how words relate to one another. This is quite a tedious and slow process. And you'll see this again and again across text analysis, that a lot of the resources that are created have taken years and years. There are some grammars, when we get to talking about syntax, there's some grammars that have taken like 30, 40 years to be created by hand. And some people, it's their labor of love doing this. But a lot of times there are potentially other ways that you can get to similar information. Can we do this in a more automated way over large amounts of data and thus avoid a lot of this manual effort? So the human annotation itself is not always super reliable. People can make different judgments, say, on semantics. And there's a lot of sort of corner cases and subjectivity that makes it complicated. So if you are going to get things manually constructed, you need to get experts to do it. Or you need to get a whole lot of people who are using their linguistic insights, just being a language speaker. So typically that adds to the expense in that you either need to get it redundantly done by many or done by very expensive experts. So another problem is language is dynamic, it changes over time. You see words like random things coming out of Trump's mouth and his cronies. You see things coming out of social media, things like hashtag and so forth. You see new slang and all of these kind of things. You see new senses of words. Language is always changing. And oftentimes words get reappropriated to have other meanings. And in order to capture that, we need to keep manually updating our language resources, like our WordNets and so forth, which adds to their cost and means that at any point in time, they're always a bit out of date. So I'm not sure when the most recent WordNet was released, but I think it's still several years old. And I reckon you would take you about a minute, well, maybe even less, to find words that it's missing that you would use on an everyday basis. So its coverage is never going to be that good. It's only ever going to cover a subset of the lexicon. So then the big question is, can we just look at text? Can we look at text collections to try and obtain word meanings automatically rather than doing this all manually? And in particular, trying to leverage, say, Google is sitting on a scraped version of the entire web, well, of the accessible web, which might be 20 or 30% of all the data out there on the internet, and that's what they use to index. Can we use all of that collection of text, so petabytes of text, to try and learn these kind of things? And that's the idea behind distributional semantics. So the idea here is that the meaning of a word is based around the company it keeps. There's this classic quote, I think this is from the 1940s, 1950s, with the idea that we can characterize meaning based around finding that word in context. And the idea is that other words that appear in similar contexts are likely to share similar meanings. And this is an intuition that everyone has as a language speaker, as a language learner. When we see a word that we don't understand, we look around for other signals, and we can often piece together its meaning without really needing to resort to a dictionary or asking an expert. So document co-occurrence is one signal here. So that the two words appear together in the same document might be informative about their meaning. So words like voting and politics tend to co-occur together a lot. And therefore, we might expect that there's some aspects of their meaning that's related. Now, local context is another thing, and this is the focus. Well, so we're going to talk about methods that are focused on document context and local context. The local context is going to tell you a lot about the word semantic class, also the syntactic class. So eating a pizza, eating a burger, we can see that these two words, they're occurring in the same context of eating. They have a determiner before them. This is a signal that they might be talking about similar things, in this case, food items. But let me show you a more fleshed out example. I have no idea how to pronounce this word. If we have this unknown word here, starting with T, as shown on the slide, I'm not even sure what language this is, actually. It's a European language of some kind, I think. Anyway, and we have a few instances. So we see this word in 4 different contexts. A bottle of something is on the table. Everyone likes something. Don't have something before you drive. We make something out of corn. Now, from that, those 4 sets of instances where we see this mystery word, you can pretty easily deduce that it's an alcoholic drink, right? Just as from our understanding of language and understanding of the semantics. Now, if we were to look at other words that occur in the same context, we're going to find that the word loud doesn't appear in any of these contexts. You can't have a bottle of loud is on the table and so forth. Motor oil can occur in the first one. It can be put in a bottle. It can be made out of corn, and so on and so forth. There are various other words here. This is a contrived example, of course, right, to illustrate the point. But we see here that of the different words, we see that wine can occur in the first 3 contexts, but not in the last. It's made out of grapes rather than corn. But based around this, we can simply just see that of these different words, loud is very unrelated. It can't occur in the same context. Wine is very related. It occurs in most of the same contexts. So from this, we can deduce that the meaning of our mystery word is very close to the meaning of wine. This is the kind of clue. So this is the idea of distributional evidence, that the distribution in which the word occurs, so these 4 different sentences, are evidence for its meaning. And I was hiccuping there because I was trying to make sure that I was saying the right term, distributed versus distributional. So often you talk about them together, distributed and distributional semantics. Distributional means you're interested in how the word occurs in context. Distributed means that you're talking about vectors now. You're talking about representing words as numbers in a vector space. So this is a form of dimensionality reduction of some flavor that's going to then represent our concepts. And we use the term distributed to say we're not representing them symbolically. We're not saying this is an instance in WordNet. That's a symbolic representation. Instead, we're having a numerical representation, and that's what we call distributed. And the term distributed, I think, comes about from the neural analogy that the representations that we have in our brain concepts are actually represented by different synapses firing, different neurons firing in different places in the brain. And when we see something, for instance, our way of processing that is firing many thousand different neurons, and that way the representation of what we're doing, what we're thinking, what we're seeing is actually distributed across our brain. Which means that if there's any problems, if there are any mistakes and so on, it can recover from these mistakes because we have it represented very redundantly across our brain. So based around the slightly tenuous analogy of a vector representing the brain, this is a similar idea, and that's what we're trying to get to with this meaning distributed. Okay, so we're going to cover both count-based methods and neural methods for encoding these kind of representations. So first we'll start with the vector space model. It's going to look pretty familiar. So we're going to try and represent meaning as a vector, and we're going to be considering documents as our context in the first case. So it's one matrix. It's the term document matrix. It's exactly what we've seen before from web search. We have words. In this case, each of the columns correspond to a word, a term, and each row corresponds to a document. So here they're just numbered documents, say document IDs. So, okay. So words we can represent as a column, and that's going to be the thing that we're most interested in today's lecture. Whereas before we were interested in documents and comparing documents. But it's the same matrix, and it's the same way we're going to process it in many steps. So first we're going to, instead of just using counts, we're going to do the standard things of using TF-IDF and other ways of scoring them. We're going to then use this, and this is the step that we haven't done before. We're going to then use this to produce low-dimensional vector representations because our term document matrix is very large and very many documents. We want to reduce that to a smaller, more manageable size so that then we can actually have a general representation. Okay. So I won't go through this in detail. I've just got it here for completeness. We don't just want to use counts. We'll use TF, we'll use IDF, and we'll end up with new values, say, in our document. So now we have a term document representation where every cell is a TF-IDF value. Okay. So there are problems here. If we're going to just use this directly, the term document matrix is very sparse. There are going to be some, especially if we have tweets, say, there are going to be very few words in each tweet. So that's each of our documents. Each word is only going to occur in a few of these tweets. So it's going to be, it's going to have problems with sparsity were we to operate with it directly. So what we'd like to do is we'd like to create shorter, denser vectors that can represent the information in this matrix, but in a more compact way. So this makes it more practical for doing things with it later. We have fewer features to work with. And it removes some noise, so it's sort of forced to generalize and doesn't model the data quite so well, but it can do that in a way that generalizes well by not describing, say, a 0 versus a 1 might not be so important as describing a 10 being an order of magnitude larger. Okay, so the method that we're going to use for this is singular value decomposition, or SVD. Hopefully you've seen things like this before. It's a flavor of eigenvalue problem. So the idea here is we have a matrix, which we're calling A. It's our term document matrix, say. It could be lots of different things. It's a rectangular matrix. It has size, vocabulary, times number of documents here. So the number of terms is one dimension, the number of documents is the other dimension. Okay, and what we're going to do is we're going to factorize this. So this is what singular value decomposition will do. It will say that we can represent this matrix as a product of three matrices. We have one matrix that is effectively, well, sorry, let me talk about the one in the middle. The one in the middle is giving us our eigenvalues. It's a diagonal matrix. And the one in the left is giving us a representation of each of the rows from our original matrix in a vector space, in a matrix of here width m. And similarly for our terms, our documents, sorry, we're also representing them in this last element as something of size d by m The thing in the middle is basically telling us how each of these M components, which ones are the most important in ranked order. So what SVD is going to give us, it's going to basically give us this decomposition. It's going to give us an orthogonal matrix U, an orthogonal matrix V, and a weighting for each of the dimensions, which is the values, the singular values. Now, this is similar to a lot of other eigenvalue problems. It's just a specific type of one. And it's the kind of thing where there's a one-liner in most statistical programming packages like NumPy and SciPy, which will basically spit out the decomposition. There's a few caveats, which I'll talk about in a sec. Okay, so once we've done this, we can do this exactly. We can basically take our big matrix and we can refactorize it as follows. It hasn't actually done anything that useful for us now, but the interesting thing is if we look at these values, they're diminishing, and if we are to truncate at any value of M and effectively zero out a quadrant of the singular values, we end up with a lower dimensionality, lower rank approximation of A. So the cool thing about this is that we can truncate the outputs. So how do we do this? We basically truncate parts of U and parts of V, and that will produce the best approximation with that rank, with that many parameters to our original matrix. Now, it's going to not, if we multiply it back to try and work out what the term document matrix it thinks should be, it's going to get it wrong in some ways. Once we do this truncation, it's not going to get the values perfectly, but it's going to have the minimum squared error. If we talk about the squared distance between the reconstructed matrix and the original matrix, the Frobenius norm, then we'll end up having the minimum based around that rank. Yes?
What's the intuition of what the eigenvalues mean in this context?
The eigenvalues are meaning how important each dimension of the embeddings learnt are. So in terms of text, it's kind of hard to say. It's very hard to interpret these. Usually, the point is that we're ranking them in order of importance. So if we throw in, bearing in mind that every dimension is orthogonal, if we are to throw away the lowest valued ones, then we're throwing away the things which have the least import in modeling the problem. So, I mean, it's more of a mathematical motivation. I don't really have an intuition as for what they actually mean in terms of language concepts or so forth. So yeah, it's not the most satisfying answer, I guess. Yeah. Okay, so what we tend to do is we tend to truncate. We end up with a low, and once we do this, we end up with a low dimensional version of each document, and we end up with a low dimensional version of each term. So just giving you a little picture here, we have, this is our U matrix. It was V times M. And now we're going to truncate it at K less than M. And similarly, this is just showing you the output. We'll do the same thing with V potentially if we're interested, was it called V, the other one? Yeah, it was. If we're interested in the document representation. However, here we're interested in the text representation. We're interested in each representation for each word. Each word's going to be a row in this matrix. Okay, so in the notebook, which someone was telling me I hadn't uploaded properly, now I have. In the notebook, you can see this used in practice on the term document matrix to get, in order to get representations. And these representations are effectively encoding the, well, you can think about if you think about what's happening with each document, you're learning vectors to represent each document, and then you're learning compatible vectors for the words that appear in those documents, such that when you multiply them together, you replicate the term document, or the entry in the term document matrix for that pair. So this is effectively what's happening. Okay. So that's the idea of using SVD over the term document matrix. We can actually do it over other matrices. We don't have to just do it over term documents. When it's done over term documents matrix, it's called LSI, latent semantic indexing. You may have heard that term. I probably should have included it in the title of one of the slides. But we can also, when we apply it, we often also apply it to word-word contexts. which is a different setting, right? So in this case, we don't care about the document identities. We just care about words being near to other words. So what we might say is, for each word, how often within a window of 10 words does it co-occur with each of the other words in the vocabulary? So in this case, the word state tends to have the word the near it. They co-occur 1,900 or so times. State has country near it roughly 10 times, exactly 10 times in our data set. So in this case, instead of just looking at document co-occurrence, we're talking about words within a window. And now this matrix is V times V, which is quite large. And we have to think, carefully, like what we were thinking about before, that we had problems with the term document matrix. We had to adjust things by IDF and TF and so on to stop very large values dominating. We're going to do the same thing here to make sure that it's amenable to then being further processed. So pointwise mutual information is one way to do this. So we have two events, and we're going to try and work out the likelihood that both events occur, so a word and its context word. How likely are both of them to co-occur versus how likely are each of them to occur individually? And have we seen PMI before? Have we? Maybe we, I don't know. And most people, I think, have. Anyway, so it looks like this, right? The probability of seeing the two things together divided by the probability of seeing one, probability of seeing the other. So it's a measure of the information between these two events. If they're completely independent, then we'd expect the numerator to factorize as the denominator. So it'd have value 1. The logarithm of that would be 0. If they only ever co-occur and that describes all of their individual occurrences, then we'd have a very large value of PMI. Or would we have an infinite? I'm not sure. Anyway, so I'll show you an example of it in practice. So in this example where we had the country, hell, state, fun, heaven example, if we look, now these are of course all fictional numbers, but the idea is that if we sum up all the instances and we work out that there are this many words in total in our entire corpus, which I believe is the sum, which would be the sum of all of these numbers, and then we work out basically the normalizing each of these counts in each of these cells by this total count of the number of events. And that way we can end up getting this probability of the things co-occurring versus the probability of them occurring independently. And if we do this for state and country, we can see here state and country co-occur 10 times over this denominator, so we get this fraction. X, which is state, occurs on its own 12,786 times. So again, we get this fraction. And Y, being country, occurs 3,617 times. So notice that one of these is relative to the columns and one of these is relevant to the rows. And then we can plug them into the formula and get a number for the PMI. So this is basically allowing us to quantify the information in seeing one of how likely we are to see the other. How much information? Oh, what happened there? Just ran out of power. Someone didn't plug this. Okay, that works. Cool. Okay. Can I still be heard at the back? I'm sure this one works quite as well as the other one. Just holler or something if you can't hear me. Okay. So PMI does a reasonable job of capturing these kind of interesting semantics. So we can see here that the very low values indicate that they're pretty independent events. Hell and state, fun and the. We can see that stop words like the tend to have fairly low PMI against other words. And we can see here that things like heaven and hell it's done a pretty good job to work out that they're related terms. They're likely to co-occur in a context. That one is going to be very informative about the other one, because they're often used sort of in contrast to one another. It biases towards rare words, which is a problem, and it also has this problem that there's an infinity, a negative infinity in this cell, right? Because it was a 0. We get log of 0. It's a bit of a problem. So in practice, people start hacking. You zero out all negative values, and you call them all zeros. They're rarely informative that we have a negative PMI. A negative PMI would mean that seeing one word means the other one becomes less likely. There are some instances where this might happen, but they're so infrequent and they're very rare to actually find in practice that they're not really going to be captured. So if you see the word football, you're unlikely to see the word soccer, because the context where you talk about one is going to be tailored to a certain audience, and the context for the other, you're likely to be tailored to a different audience. But even so, I think the PMI between them is still going to be positive, just based on general usage and the fact that they're listed in other documents that aren't solely about the one sport. So yeah, typically what we do is we get rid of them because they're mostly noise, the negative values, and we get rid of the negative infinities as part of that. They all get set to 0. And sometimes we might smooth rare events to try and stop them from dominating the probabilities. So we can smooth all of the probabilities like we did in language modeling. There are a whole lot of different ways of doing that in order to make this better behaved. Okay, so now once we've done this, we can plug it in, we can get our vectors using the same technique as shown before, this SVD method. We can get vectors. And if we're doing this for IR, maybe we're going to then use them to try and say, here's a low-dimensional representation of a document, here's a low-dimensional representation of a query. How similar are they? Gives us a more general way of comparing the two, with the idea being that it's not going to get too fixated on getting words exactly right. If it gets words that are similar, then that would be okay, right? So if we had a word film versus movie, it's not going to care that much. It's hopefully going to have reduced them to similar points in the vector space. So the documents that contain one or the other of the words are going to be represented in similar points in the vector space. So in text analysis, we often use it to find synonyms. So we can say, for this word, please tell us other words that have related meanings. And we can just look and say, okay, nearest neighbor, tell me what the nearest neighbors in vector space are to a given query word. You'll see a few, and odds are they're quite related in meaning. So if we search for a word like fishing, we might find words like fish, fishes, angling, angles, and so forth. And they typically end up being very close together once we do this, because they tend to occur in similar contexts, and that's the kind of thing that's being distilled as part of the vector learning. So we can use that to automatically create lexical resources. So like WordNet, we could use that to augment WordNet with new links between words. We can use it for knowledge-based population. So if we have a knowledge base like, if you look at something like the Wikipedia info boxes, right? They've got a whole lot of structured data in them. Oftentimes, we're actually interested in looking at text and seeing whether or not we can automatically predict that, say, Barack Obama was born in Hawaii or something. And can we actually see instances of that in the text? And a good way of being able to do that is doing this kind of vector learning, looking at words in context and being able to then generalize and make these predictions. There's a bit more mechanics and machine learning on the way to actually realizing that gain in a knowledge-based setting. Okay, and then the really common use, the predominant use of these is saying that now we have representations of words that we can then use in other processing. So if we know now that we have a representation for movie, it has a vector. We have a representation for film, it has a vector. We can treat this vector as our input. Rather than saying that this document is a bag of words, we can treat it as a bag of these vectors. And if film and movie end up having a really similar vector, then the model is going to be robust to different word choice. And that's often how they're used in practice. Yep?
You gave an example comparing words versus words, but you also talk about words versus documents.
So you
How do you use that over
You could do that, but most of the time it's documents versus documents. So, but the point is that the vector for the document is going to distill the word usage in the document. That's the information that's being... if we're looking at what's happening with the SVD, effectively it's... Where was it? Effectively, each document is it's getting a fingerprint for what kind of stuff it tends to have in it. And each word is getting a fingerprint for what kind of documents it tends to occur in. And that's what these vectors are representing. So if we have a lower dimensional representation of our document, we can also get a low dimensional representation of a query, pretending that it's also a document. And doing the same. You can actually compare things from one to the other, but by and large, you're talking about things using either one side of this or the other, not both. That makes sense. Okay, so the other mechanism for learning these things are using a neural network architecture. So SVD is one way of solving things. SVD is this way based around matrix decomposition, and neural networks are other ways that we can learn these kind of representations. So this is often called deep learning, neural networks, various other names. And so the models we'll talk about is this idea from Google's Word2Vec. They have two models, the skipgram model and the SIBO model. And I'll talk primarily about the skipgram model. So this is a paper that came out, I think, in 2013, 2012, 2013, which made quite an impact, showing how we could basically distill and get very, very good word embeddings at very large scale that had very impressive properties in terms of distilling semantics of language. And it's based around this idea of learning a classifier, learning well, they call it people often call it deep learning, but it's not really that deep. It's a fairly simple classifier, and it's based around this idea of distilling their context. So the idea is we're trying to learn vector representations of words that are similar to the vector representations of the context in which they occur. And it's more similar to that than it would be to a random word that doesn't occur in the context. And this is the idea that's then operationalized into an algorithm for training. And the way we describe similar versus dissimilar is the dot product large or is the dot product small? And then that's the training signal that's used to parameterize a classifier to then try and learn this. And the point is we're giving it a very large collection of text and we're asking it to learn what are the vector representations of a word, both if they're a center word and if they're a context word. I'll go through in a sec what that means. So skipgram, just illustrating, we have this idea, we have this sentence here, we have a center word that we're going to focus on for the moment. We're going to walk this through our corpus one word at a time. But if we're looking at rests now as our center word, we're going to then try and predict all of the words that surround this word. So given rests, we're going to try and predict life, he, in, and peace. These are 4 positive examples of words that occur in the context. So you can think of this a bit like a language model, right? It's like a bigram language model. It's just it's not running left to right anymore. It might be predicting 1, 2 to the left, 1 to the right, 2 to the right, so forth. But by and large, you can think of it as a bigram language model just trained in a slightly quirky way. Okay, so that's called the skipgram model. The SIBO model is contextual bag of words. The idea is that you get the bag of words of all of the neighboring words, so the 4 words shown in green, and we try and predict the word in the middle. So this is a bit like a language model, except we're not just working left to right, we're working outside to inside. But were we to get rid of the in piece, now it starts to look a lot like a language model, right, that we've seen before. Okay. And so the local context usually means words within a few positions of each word that we're looking at. in the example it's 2, in practice it might be 10 or so. So we're looking largely within the same sentence, or at least closely the start or maybe of neighbouring sentences. Okay, so if we do this, we can express the total probability of the context around this word here. Say, we're just going to sum out over all of the different context positions, -2, -1, +1, +2, and work out its probability. And this is the signal, well, this is the signal that training will be trying to optimize. The way we frame each of these probabilities is using this expression here. So this looks a little bit like a logistic regression classifier that you will have seen before. A logistic regression classifier, you have an exponential of a linear expression, a linear form in the numerator, and then you have some normalizer to make it sum to 1. Now, you notice here that something strange is going on. It doesn't look quite like logistic regression. There's a dot product in the numerator, and this is where it sort of differs. So we're saying the probability of seeing word K given word J is based on the dot product between their two representations. So context or center word K is a vector, C sub WK. So we have a big matrix C, which has all of our representations of length K, or length D in this example, in the next slide. And we also have a big matrix of representations for each word in context, that appear in context. And so we're going to look up both of those words, and we're going to dot product them together. That gives us a score. The exponential of that score is then going to be rescaled to give us this probability. And so as we train this, it's going to try and learn to upweight the dot products for words that co-occur together a lot, and it's going to downweight the dot product for words that don't co-occur together a lot, because that's going to bring down the probability of the true things. So effectively, it's a logistic regression classifier over a sort of slightly weird-looking bigram language model. That's not how they presented it in the paper, though. And so what are the parameters of this? There are two big matrices. There's one which is, have I got my notation correct? Wait a sec, I called it C and V here, and now I've called it W and C. I'm sorry. That was my mistake. Yes, sorry. Oh, I thought you were about to ask something. I was just so used to it. Okay, so there are two big matrices. There's one that's of size vocabulary times D, another one of size vocabulary times D. These are the, okay, let's not worry about that subscript there. I'm not really sure the subscript of V being that important. The point here is that for each word in the center, we have one embedding. For each word in the context, we have another embedding. And when we look up a given word, I, we're just reading off a row. When we look up a word J, we're just reading off another row. And then we're going to dot product them together, get a score, and that'll tell us the compatibility between word I and word J, how likely they are to occur in context once we throw them through the formula. Okay, so you might see these kind of diagrams. I find sometimes these diagrams are more confusing than helpful. You can make what you will of it. But the point is, it's trying to illustrate we have an input, which is a word. In this case, it's a vector of size vocabulary with one of them on. So it's a vector of a whole lot of zeros with one value set to 1, which is basically an indicator feature saying this word occurred. Okay, so this is saying that this is our center word. Our center word, say, was word J, and that value is 1. The rest of them are zeros. Now, if we multiply that through by our big matrix W, all we're doing is reading off one of the rows or columns, depending on if we do it on multiply on the left or the right. So the point is multiplying through by this one hot input by a matrix is effectively just indexing one of those elements of the matrix, one of the rows of the matrix. That gives us our representation here. Then we're going to multiply that through by the matrix C. That's going to now give us a whole lot of scores for each of the output words, which we're then going to renormalize using this exponential and then normalization factor. So that's the softmax transformation shown on the previous slide. Now, in order to generate the word to the left and the word to the right, Now, obviously, we might do this for the word 2 to the left and 2 to the right and so on. It's just showing here 1 to the left, 1 to the right. But we're using the same transformation. So we're basically getting what are the probability of all the words occurring anywhere in the context of this. And this is trying to illustrate that it's the same distribution used for each of the words. Okay. But yeah, if you find that figure a bit complicated and strange and confusing, then I would just skip over it and read the mathematics, because I think they're a little bit more clear about what's actually happening. Okay, so how do we train this model? So I was saying before, we try and train it so the dot products are close together. And that's a way of maximizing the probability of the text. Now, anyone who's come here from statistics will be like shuddering, because you're maximizing the probability of something given its left and right neighbors, and then you're maximizing the probability of its neighbor given it. It ends up being this monstrosity that's got no real grounding in any real model. It's kind of a dirty model in that respect. It's degenerate, but it works really well, and that's the motivation for why people do it. It's if you were to actually make it a valid probability model, you'd end up with something that looked more like a language model that worked left to right, so it obeyed the chain rule. This does not obey the chain rule. This is more like what's called a pseudo likelihood estimate, if you've seen that before, but yeah. Now in practice, the way I presented it before, saying that we're treating this as a language model, we could do that, but we find that that's actually really slow. So if we come back, each of these probabilities requires a sum out over the entire vocabulary. That's often a very big number. We have to do a whole lot of dot products and exponentials in order to calculate that. That's too expensive, and it wouldn't scale to large data sets if we were to do that. So instead of doing that, we're going to do a fairly standard trick, which is, instead of trying to predict the words themselves, we'll try and predict, is this a word that we've actually seen in context, or is this a random word? And so I'm showing you an example here. So if this is our context here, a tablespoon of apricot jam, a pinch, and our center word is labeled here with T, our target word. This is going to be our set of positive examples. So we're going to say, we're going to have the pair apricot tablespoon, apricot of, apricot jam, apricot A. So those 4 instances are going to be positive examples, and then rather than looking at the entire vocabulary of stuff that could happen, we're just going to randomly sample another, in this case, another 8 examples. So we're going to have aardvark, puddle, where, coaxial, 12, hello, dear, forever. These are words that haven't co-occurred with apricot. They're just drawn at random from the vocabulary, and that is going to then be treated as negative examples. And then we're going to try and learn a classifier that's basically saying, are these 2 words that we should have seen together, real words that we've seen together, or are they fake examples that we inserted using this random process? And so this then becomes very tractable, because we only add a tiny handful of negative examples rather than tens of thousands per instance. Yep. So you're sampling at random from the vocabulary according to the unigram frequencies, by and large. There's a few hacks people do, but at a rough level, that's what's happening. So you're sampling just unigrams, and then you're saying you're treating that as a negative example. Now, it could be that you sample a word that would actually be valid in that context, but the chance of you doing it is so low that it's assumed to be not a problem. So, yeah. So then training becomes training a binary logistic regression model. It's still got this little dot product in the middle, and so we can think about these two approaches as being very closely related. This is kind of like an approximation of the previous idea, but one that scales very well. Okay, and so this is what's implemented in Word2Vec, and this is what's implemented in various tools that you can have a play with. Okay, so just to illustrate what's going on, training is an iterative process. It frames this binary classification likelihood, and it makes a gradient descent step each time it sees a small batch of data. That's like a word with all of its context and all of its negative examples. And each step is going to try and move the embeddings closer together for words that were actually in context, and it's going to try and move the words apart, the vectors apart for noise samples. So if we look, so it's going to basically say apricot should be a long way from aardvark, because that would maximize this, the probability of this being a negative example. And we're going to try and move apricot closer to tablespoon and apricot closer to jam and so on, because that's going to maximize the probability of this, of it being a positive example. So again, this has a lot of parameters, this model. It has these 2 mega matrices. They have potentially millions of parameters on any real data set. We're going to have to try and, so basically this is the mechanism for doing the updates. Okay. So once we've learnt these, how do we know they're any good? There are various different tasks out there for testing them. And what we're going to test is basically saying, if we get a word pair, how different are they using cosine distance, say, cosine similarity? Are they near to each other in vector space? Are they, you might test to say what their distance is, or are they within the k nearest neighbor for a small value of k? And now there's a whole lot of tasks, a whole lot of data sets that have been created saying, here's 353 word pairs, and humans have sat down and said, these words are very similar. So you'll have a whole lot of really strange things, right? So you might have coat and jacket, yes, very, very related. We'll get a score of 1 in relatedness or 0.9 in relatedness. We get something like smoke and fish, you might get a 0.5 because they are related concepts in some contexts, but they're not that similar to be a synonym. And then you get, I don't know, boots and university or something, which hopefully should be somewhere low in terms of relatedness. So there are various of these things. There's ones for nouns, WordSim 353, ones for verbs and adjectives, other ones that ask the multiple choice question from a language learning test saying, please tell me words that are close synonyms. Here's 5 examples. And that's, you can then get the model to predict and say, well, based around your vector distance, which of these multiple choice answers was closest to the query? And answer it automatically. And so these models actually do very, very well on these tests. I don't have any numbers here, but you can read about them in the readings. But one of the more interesting things about this, hopefully you can see this up the back, is that there's an interesting geometry to the word meanings that are learnt this way. And what we see is that, so in this example on the left here, I probably should have attributed this figure. I think this was from the glove paper a few years ago. We see here are words like brother and man and uncle. They're close together in this vector space. I should say the vector space has probably 300 or 1,000 dimensions. This has been projected down to 2 for the sake of drawing in a figure. There are mechanisms for doing this automatically. I'm not sure what was used to create this one, actually. But the point being is we can still see this phenomena once we project it down. We can see that words that are similar are put close together. We can see that there's also a cluster here for sister, aunt, and niece. But you can also see, and as shown by the dotted lines, gender is relatively consistent as a vector transformation in this space. So you can see that if we move down in this space, we can go from brother to sister, man to woman, again down, and so forth, nephew to niece, king to queen. And this kind of geometry is sort of one of the really surprising and very cool kind of properties that we can then try and exploit. So you can ask a lot of these analogy questions. So man is to king as woman is to what? So you can basically say, the way you test that is you say, man versus woman. There's a vector that would characterize how far apart these are and the direction between them. If we just add that on to king, we're going to get a point somewhere around here. What's the nearest word to that? It might be Earl, it might be Duke, it might be Queen. And oftentimes you actually get it right. So, well, for specific types of analogies, these sort of gendered analogies work very well. You can do it for capital cities. France is to Paris as Italy is to, and then hopefully we find Rome. And I believe we do in this case. I think for Australia you might find Sydney rather than Canberra, for instance, because it's all about text analysis. And yeah, Sydney is going to, or Sydney or Melbourne perhaps, is going to have a greater footprint in the data set. Okay, and yes. And this example on the right is showing another thing that if you look at different lexical forms of a word, so dark, darker, darkest, you can see that there's a pattern from getting from one to the other to the other. There's a sort of fairly consistent geometry about moving between each of these related forms of words. So you can do some morphological analysis of words, like derivational and inflectional morphology, using these kind of word contexts alone. And this is really quite surprising because, you're just basing it on the words to either side, right? The co-occurrence patterns, the distributional evidence. So it's pretty amazing that you can find a lot of this information. And if you want to understand why you get this information, there is a bit of evidence in the literature about how this comes about. I won't go into it because it gets a bit technical. But I'm happy to answer offline. Okay, so how do you evaluate these things, right? So yes, you can evaluate them on these word similarity lists. You can do these kind of fun analogy tasks, but they're not really potentially that useful to any real end user. They're just fun. In reality, the main use for these things are in downstream tasks. So if you wanted to develop a sentiment classifier, you wanted to develop a question answering system or a tagger or whatever, you might want to use the embeddings as input rather than using the words as input. So rather than using a vocabulary of 50,000 words as input to your sentiment classifier, instead you're going to have this 300-dimensional vector. So you've cut down on the parameters that you need in your model, which is great, because you went from size, whatever it was, what did I say, 50,000 down to 300. And that means that you can now potentially do a lot better from small amounts of data, which is a great opportunity. And it also means you can sort of do a bit more modeling innovation in your task as well, potentially, in that you have this rich representation which has this interesting clusters and geometry and so on. And if your model can capture that and use that in classification, then that's great. And usually the models that are doing that are deep learning models. This is the initialization step that's very commonly used in many deep learning models. So you'd learn, well, actually, you'd download off Google their lovely, very large and exhaustively trained vectors that they've trained on most of the web, and you'd use them as representations. You'd then develop your model on your data using those as your input representations. Now, you may have heard of some other stuff more recently, and this is getting very recent within the last sort of 8 months or so. A system came out called Elmo in the Sesame Street theme. Google AI a few months later released a system called BERT. They're both around the idea of learning a deep learning model that has as part of it these kind of embeddings, and they're framing the learning problem a bit differently to what I was saying, but by and large they're similar flavors to what we're talking about here, except the main difference is they're not looking at just words alone, they're looking at words in context. So they can embed a word given that the sentence surrounding it has given words. So if you have a whole sentence as input, you can throw them into Elmo or BERT and you can get a very, very good representation which can do extremely well in many other downstream tasks. In fact, so well that people don't, I think, really understand why it does so well. But yes. And so these are other things that have been trained using, I don't know, several months or years of GPU hours at Google or Allen AI Institute or various other places, and you can then, they've released these things for the community to use, which is great. Okay, and let me just point to some software, and I'll finish up there. except to say that there's reading about this, and I'd recommend you have a good look. There's 2 readings. There's a more formal one in Eisenstein, and then there's a less formal one in Jarofsky. They're both pretty good. And please, raise any questions if you have them.